Okay, so we have found that our gamma function was well defined for x strictly greater than 0, so x in r plus star. Now let's have a look at the continuity of this function. Okay, so we want to use the theorems of on continuity of parameter-dependent integrals. All right, so continuity. Let's see, what do we need? The first thing we need is that we have continuity in x of the inner function. So that means that the function that for x gives you t x minus 1, sorry, t x minus 1 times exponential of minus t. Well, we have no problem about this because that can be rewritten as exponential of x minus 1 times the log of t, e of negative t. So for all t that belong to 0 plus infinity, there's no problem that this is a continuous function in x, right? So no problem because it's just some exponential of x times a value, right? So that's continuous. Next hypothesis, we need that the function which to t gives you, well, the same stuff, right? T x minus 1 e of negative t is integrable for fixed value of x. But actually, this is exactly what we did earlier. That's what we did. We did it before. That's what we did when we wanted to, when we showed that the domain of my function was r plus star. That was exactly showing the integrability of this function in t. Okay, next, as always, going to be the hardest part, is finding a dominating function. Okay, so what's happening for this one? We need to find g of t, so independent of x, such that it's going to be bigger than this t, x minus 1, exponential of negative t, so for all x, and for all x greater than 0, and for all that should stand for all t in 0 plus infinity, and furthermore, we need that the integral of g to be bounded. Okay, g has to be integrable. Okay, this is where problems begin. So let's have a look at this function. As we already said, I could rewrite this function as exponential of x minus 1 log of t, well, times the exponential of negative t. This exponential part, no problem. It's going to help convergence in any case, all right? In neighborhood of 0, that's 1, and neighborhood of infinity, that's going to make almost anything converge. Okay, now the problem happens for my exponential of x minus 1 times log of t. Or even, well, we can consider that, well, let's work on that term, the exponential of x minus 1 times the log of t, which was actually the t, x minus 1, and that I can rewrite as t to the x times 1 over t. Okay, so you see it's going to, first of all, it's going to depend whether t is between 0 and 1. Why? Okay, let's see what we have. T to the x times 1 over t. The thing about that, if I'm looking for integrability, this as such is not integrable. Okay, neither on 0, 1 nor on 1 plus infinity. So it has to be moderated. Thing is that in plus infinity, we hope that this is going to be moderated by the exponential and with the help of this one. And in 0, 1, well, the exponential is equivalent to 1, so it should be moderated to by this stuff. Okay, the thing is that if t belongs to 0, 1, we have, so you remember that if I take the power of some powers of t, let's say some positive powers, okay, and let's take 2 powers of t. You remember that the highest the power, the lowest the value, meaning that I really have that t is to the power b is going to be smaller to t to the power a. Okay, so that's what I mean. What I want you to realize is that t to the x is going to be if t is smaller than 1, that's going to be bigger for smaller values of x. Okay, and what is the smallest value of x? It's 0. But if I put x is equal to 0, which is just outside of our domain of convergence for the integral, my function now becomes my inner function in neighborhood of 0 is going to be equivalent to 1 over t, which is uh, well, it's going to be equivalent to 1 over t, but more than that, it's also going to be equivalent, smaller, sorry, to 1 over t. So that could be a good dominating function, because indeed it dominates my inner function, but the problem that you see is that it's not integrable. Okay, so as such, we can't find a better lower bound for the x, then well, 0 is not going to be a good lower bound. That's just outside of our domain. And similarly, if t is greater than 1, and I write t to the x and, well, divided by t times exponential minus t, so that's it. The thing is that, all right, the exponential moderates a lot of things, but what if I take x goes to infinity? What's happening? That may be a problem. So that's e of x ln of t, okay, divided by exponential of minus t. T times, all right? So the thing is that I've got two exponentials, and potentially t is bigger than 1, so it could go to infinity, and similarly the exponential could go to infinity, and the log is positive, so I have two exponentials competing. So that's also going to be a problem. So how do we get rid of that problem? In that case, it's going to work. We use the extension of the theorems. We consider x that belong to any closed interval in R plus star. Okay, so the lower bound a can be as close as I want to 0, but not 0, and the upper bound b can be as big as I want, but it's not going to be infinity. In that case, it's going to be much simpler to find a dominating function. So again, we're going to build our function t in two parts. One part for t strictly smaller than 1, and one part for t bigger than 1, right? So we said that when t was smaller than 1, we needed to bound from above t to the power x, right? But if x is bigger than capital A, then that's just going to be smaller or equal to t to the a, right? If t smaller than 1 and x bigger than a, right? So let's just keep e to the a minus 1 times log of t. Well, even we can just write it with the original writing, so that just makes t to the power a minus 1 times exponential minus t. That's going to be our g. And similarly, when we get t to the x, it's going to be smaller than t to the b if t is bigger than 1 and x, sorry, is smaller than b, right? Smaller or equal. I can use large inequalities anyway here. So I get, I can choose for my dominating function t to the b minus 1 times exponential minus t. And now what do we have? We have indeed a dominating function, and we furthermore we have a and it is integrable. Okay, so that we can see that again for the same arguments for small values of t, so for t between 0 and 1, the a minus 1 is going to be, as a is strictly bigger than 0, that's going to be the exponent of t is going to be bigger than negative 1, so that's going to fine. And to work fine, the exponential is equivalent to 1. And the second case, well, the exponential is just going to win over the polynomial, and so that it's going to make a converging integral. Okay, so that was a bit longer, but still it worked in the end. We just have continuity because we could check all the hypothesis of the theorem, but as we couldn't check it on the whole, well, strictly speaking, on the whole R plus star, we considered X that belonged to any closed set included in R plus star. Okay, so that's fine. Okay, why is that? In the end, is that working? Well, in plus infinity, actually, okay, my function is going to may become infinite at plus infinity. What I just need is that it's well-defined and continuous for any fixed value, okay? And until I reach infinity, it's going to work. And that's why what the B stands for, okay? It can be a very large value. It's still going to give you something continuous. We can still very well define it and continuous. And the lower bounds, well, it's just that we had an open lower bound as 0, but the 0 value just makes everything fails. It's just that, but as long as I'm just a bigger than 0, it works. So that's what this closed lower bound expresses. Okay. So I encourage you to look at, well, I'm going to put online the correction of the whole problem about the gamma function, so I encourage you to look at it because, well, I agree, it's far from trivial, but it's going to address a lot of nice and interesting points about this kind of integrals. Okay, so just to complete our study, we should really see that we have a very similar theorem for differentiability. Okay, so for differentiability, we indeed can extend the conditions to anything that, sorry, I've lost my pen again. For differentiability, if you have problems finding the dominating function, g, you can also, sorry, I've really lost my pen for the time being. So you can really just work with any closed interval on inside of your domain. So any closed interval in I. Okay, good.